Hello, hello, everyone. Welcome to another Sunday tutoring session. Thank you so much for being here today. Chris is saying, woohoo, let's do this. I'm so excited that you guys are excited to actually do chemistry on a Sunday. Now, that just shows commitment that you're here, and as well as just kind of that practice that we all need. Something that I wanted to mention is for you guys to not have to repeat the class again or to really just master these concepts of chemistry. It doesn't just take one practice problem or even just one 3-minute video. Really, what it takes is for you to actually sit down and have a lot of practice problems, maybe 10 or 20, depending on really, how many you need. And you just annihilating those practice problems to the point where you don't get it wrong anymore. That is true mastery, or really just understanding the concept. And I truly recommend that for everybody, because that is what's going to make you not only pass, but succeed in general in chemistry or whatever class you take in the long run. All right. So I also wanted to talk about kind of where we're at right now with subscribers and the cool thing that I'm doing. So right now we're still growing in subscribers. Thank you so much for everybody who's been sharing my videos and spreading the word and spreading the knowledge of chemistry. So I really just wanted you guys to kind of, to thank you for that. And as a thank you, as you know, I am doing these live tutoring sessions as a huge thank you, because I do work full-time. I am a full-time tutor. This is my profession. I typically charge anywhere from 40 to 60 an hour. And I'm doing this completely free just because you guys are subscribers. And I truly appreciate that. I truly appreciate you guys spreading the word. Now, please continue to spread the word, because we haven't reached that 10,000 subscribers mark just yet. And once we hit that, I will be doing an 8-hour live long tutoring session. So yes, you heard that correctly. 8 hours of live tutoring where you can come in with all your questions and just annihilate those questions and really just get that final down. Because I know that tends to be a lot of your grades. Some people, it's 20% of their grade. Others, it replaces a whole test score, or actually 2 test scores. So the final is extremely important for you guys to just get down. All right. So why don't we go ahead and get started today? Today, we are focusing on different types of reactions and molarity. So the first thing that we're going to focus on today is a precipitation reaction. Then after that, we're going to get into acid-base neutralization. We're also going to get into kind of balancing equations. And lastly, we're going to end with molarity, just in case there's a specific topic that you want to get to. The topic, kind of that order, this is what I'm going to get into. So molarity is at the very end, if that's what you're waiting for. Precipitation is right now. And then after precipitation, it'll be acid and base neutralization. Let's dive in. All right. So a precipitation reaction, really anything that forms a precipitant or precipitate, I've heard it either way, it just means it forms a solid. So that's really all a precipitation reaction, that kind of clues you in what it is. It forms a solid. All right. Now, there's more to that, of course. So for a precipitation reaction, we actually have to know our solubility table. So solubility is really just saying, does something dissolve or does it not dissolve? So if something dissolves, it's soluble, making it aqueous. If it doesn't dissolve, then it's insoluble, making it a solid, or your precipitant. So let's try one. And we'll go back to understanding and remembering all of our namings and all of our charges, because this is actually a way that professors like to throw these practice problems or throw these quiz questions, are to actually give you the name and you have to build the chemical formula and the chemical equation overall. So we have lithium. Lithium is Li. Oh, I have it on the squares. So lithium is Li, and lithium has a +1 charge. And then sulfate is SO4 with a 2- charge. So can't forget our polyatomic atoms. They're going to keep coming up. So then now I'm going to balance this, and we'll see that this 2 is going to lasso or be needed for our lithium. So we need 2 lithium. This would have been Li2SO4. That's our first reactant. I'm now going to add that to calcium. So calcium is Ca with a 2 plus charge, nitrate, NO3 with a -1 charge. And then we'll once again balance out those charges. So I'm going to move this 2, and I'm going to actually place that in parentheses. So it's going to be calcium, and then our nitrate will be in parentheses because we needed 2 of our nitrate. All right, so these are just our reactants. Now let's go ahead and predict the products of our precipitant reaction or precipitation reaction. So looking at this, predicting your products, what I like to do, I like to kind of think of it like you're foiling. I know, going back to math. So I'm going to kind of call this as the inner goes with the inner and the outer goes with the outer. Now this will make more sense once I do it. So the inner goes with the inner, and then that's what's going to actually form your first compound. So remember that for an ionic compound, which we actually have ionic compounds here, an ionic compound is a metal that's positively charged combining with a nonmetal that is negatively charged. That's exactly what we have here. So our metal, or our positively charged, has to always be first, and then our nonmetal or our negatively charged element or polyatomic atom has to then follow. So then we'll have calcium. Remember, calcium's charge was 2 plus. And then now we'll have sulfate. So SO4 with a 2 minus charge. That's balanced already. So, okay, there's no need to do anything besides actually writing out the compound. And then next, we're going to go ahead and look at the last and the last, so the outer with the outer. So I just did the inner with the inner. I'm now going to look at the outer with the outer. And once again, I'm going to place that metal, or that positively charged, in front, and then that nonmetal or polyatomic atom at the end. And our lithium will drop down with a plus charge. Now, I'm going to make a note that this 2 does not come back down into the next compound. That 2 was only there to balance out the compound where lithium is going with sulfate. So it's not there to balance out lithium with nitrate. All right, so none of the subscripts come down. The only subscripts that do are the ones that were in that like polyatomic atom, like in this case with sulfate. So lithium will just be by itself, and that's a positively charged atom. And then we'll see that nitrate, that NO3, once again, this 2 does not come down. It just goes back to its normal charge of -1. They're balanced, and that is our product. So lithium nitrate. All right, so that was really just predicting your products. Now we have to figure out, is this a precipitation reaction? Is this going to be, is this going to form a solid? And then what we have to look at that is we have to understand how to use our solubility table. So let's get to that. So this is an example of a solubility table. There's so many different ways that you can see this, by the way. This is just my favorite solubility table. I've also seen it where they kind of just write it all out. Personally, don't like that, but really just depends on what your teacher or professor is giving to you. So how we use a solubility table, note that there's actually one side that is going to say that all of your ions that form are soluble. All right, so remember, soluble means that it does dissolve. So that means it's aqueous, or AQ. And then now you'll see on a different side, it says something is insoluble. If something is insoluble, it does not dissolve, so it becomes a solid, right? Insoluble, it's not dissolving, so that becomes your solid. So that's really what we're looking for. And then what I'm going to focus on first, I don't really have the states here, but I'm just going to focus on the ending portion of every single compound. So looking at SO4 or sulfate, I'm going to look on this table and see, where are the sulfates? So the sulfates are right here on the bottom. And we'll see that they're typically always soluble, with the exception. So that exception then tells us they're going to be insoluble if they have that atom attached to the sulfate. So let's look and see, is lithium part of one of our exceptions? So sulfate is typically soluble. I see here, well, lithium is not within that exception. So no, it's not going to be insoluble. It's going to remain soluble. So it is aqueous. So that's where I knew it was aqueous. And then I'm going to continue on, and we'll see nitrate. So always looking at our endings with these different solubility tables. So looking at NO3, I see that nitrates are right here. And there's no exception to the rule. Nitrates are always soluble. So, okay, I know right then and there it's aqueous. Moving on. Now, once again, we have another nitrate. We just said all nitrates are soluble, making them aqueous. And lastly, I'm going to look at the calcium sulfate. So that sulfate, we said, has exceptions to the rule. So sulfates are typically soluble with the exception of these atoms. And right then and there, I see calcium is part of the exception. So yes, it's a solid. And right there, that's how you know this is a precipitation reaction. It formed a precipitant, meaning it formed a solid. And then, of course, we would have to balance the reaction. For right now, I'm not going to balance these reactions, but for later on in molarity questions, I will be showing you how to balance equations if that's something you still need help with. So I'm going to continue on just to show you how to predict these products and just how to be able to know, is this a solid or not? So let's look at another one. Now we have aluminum chloride. So aluminum has a 3+ charge. Chloride or chlorine has a -1 charge. So balancing this out, going to lasso or bring that 3 down because chlorine needs 3. So we'll have aluminum Cl3 or chloride. And then we'll see, okay, I'm going to add that now to my next portion. So this is going to be sodium. Sodium is Na with a +1 charge. Hydroxide is another one of our polyatomic atoms, which is OH, and that's a -1 charge. Right then and there, we're balanced. Yay. So that's NaOH. And then from there, I'm going to predict the products. So once again, I'm going to do that whole foiling technique where it's going to be the inner and the inner and the outer and the outer. So predicting our products, let's look at the inner with the inner. And remember, the inner with the inner, we want that metal or that positively charged atom to combine with our non-metal or the negatively charged atom. So then I'm going to have our positively charged atom we know is sodium. So Na, that has a +1 charge. And then now chlorine is Cl with a -1 charge. Right then and there, that's balanced. So that's just going to be NaCl. And then next, I'm going to look at the outer with the outer. Remember, it's going to be the positive, then the negative. So then our positive or our metal would have been aluminum with a 3+ charge. And then our hydroxide is OH with a negative charge, a -1 charge. So then it's not balanced. OH needs to have 3 to match or balance out with our aluminum. So then I'm going to just place this 3 down, and then I'm going to show you that I will place this in parentheses because that 3 has to apply to every single atom, the oxygen and the hydrogen that's within hydroxide. So that is our new product, aluminum hydroxide. And then from here, we have to predict, all right, is this going to be soluble? Will this form a solid? And that would make it a precipitation reaction. So let's see. Going back to our solubility table, I'm going to always look at just the ending portion of every single compound. So you're really looking just at the nonmetals. That's the easiest way to approach this. Now with chlorine, it's a type of halogen. So sometimes they call them halides. That's what it has right here. It's just a different way of saying halogens. And right now we're and by the way, halides is really like talking about the actual ion itself. So looking at our chlorine, does this fall under any of our exceptions? So they're typically soluble with the exception of any of these atoms. Now, aluminum does not fall under any of those exceptions. Thus, it's soluble, making it aqueous. So aqueous. Now, I'm going to look at the OH group and look for those hydroxides, and we find them here. So our ions that are typically insoluble are the hydroxides. So these are typically insoluble. Let's check for any exceptions, though. So looking at all of our exceptions, we'll see that, okay, Na, does that fall under our exceptions? So it says when combined with group 1 or any of those calcium, barium, or strontium, or ammonium, and we'll see that, remember, Na does fall under the group 1. So yes, this is an exception to the rule, thus making it aqueous. I know it's kind of like back and forth. I'm like, oh, okay, it's insoluble, but wait, there's an exception. Welcome to chemistry, right? But if we're looking at this, hydroxide is typically insoluble. So the exception means it's soluble, all right? That's how we kind of look at this. So then that's why it would have been aqueous for sodium hydroxide. Now looking at, once again, at another OH group. So this is typically, we said, insoluble with these exceptions that I show here. And then we'll see, does aluminum fall under any of our exceptions? Well, it's not in group 1. It's not any of those ions. So no, making it still insoluble or a solid. And just to continue showing you how to use this, chlorine or Cl, that is a type of halide. Those are typically soluble. Let's check for any exceptions to that rule. So we'll see that Na is not one of our exceptions to that rule, making it soluble. So it would be aqueous. All right. I think we're starting to kind of pick up on the trend here. Let's look at one more, and then we'll move on to neutralization reactions. So looking at this, luckily they really gave us the overall formula in the beginning. Now we're going to predict the overall products. So once again, my whole little foiling trick, looking at the inner with the inner for right now, where your metal will always be first and then your non-metal. So then looking at this, we'll see our Na is our metal, and that's a positive charge. I will not bring that subscript down. That 2 right here was only there to balance out that Na with the compound or with sulfate as a whole. So that 2 does not come down whenever you're kind of predicting these products. So Na would have been just a positive 1 charge, and then we have OH. And once again, this 2 does not come down, so that's just going to be a negative charge. And then they're balanced, so okay, NaOH. And then next we'll see, okay, I'm going to look at the outer with the outer. And we'll bring down our metal with our non-metal. And then Ca has a 2+ charge. And then SO4 has a 2- charge. How nice. So right then and there, they're balanced. And that's our other product. And now we'll check for the different states and see which ones are aqueous, which ones are a solid. So looking at the first different reactants that were given, they really told us that it's aqueous. So great. Now let's just move on to NaOH and calcium sulfate. So looking at NaOH, remember, we're always going to look at the ending of our compound. So looking at OH, I'm going to go back to that table. And hydroxide is right here. And we'll look and see that, remember, it's typically insoluble with the exception of any of these atoms. So we had NaOH. So Na is in group 1, making it an exception to that rule. So hydroxide is typically insoluble with the exception of Na. So it makes it soluble. If it's soluble, it's then aqueous. So this is aqueous. And then now we'll look at calcium sulfate, and SO4, we're going to focus on the end again when we're using our solubility table. So SO4, let's look for that sulfate. Sulfates are right here. So sulfates are typically soluble with the exception of these ions. So with these exceptions, it's telling us that that's going to be insoluble or forming a solid. So in our case, we said we had calcium. It's part of one of our exceptions, thus making it our solid. So once again, this is a precipitation reaction because it does form a solid. And that's precipitation for you. All right. Move on to neutralization reactions and what they entail and what they're actually always going to form. So neutralization reactions take on the kind of form of having an acid plus a base to form a salt and water. So how do you know what an acid or a base or even a salt is? I know we know what water is, but everything else we're really not told. So my little trick for you or hint for you, whenever you're kind of looking, is this an acid? Is this a base? Is this a salt? What's going on? Is this chemistry? So looking at that, I'm going to say acid is always going to begin or start with a hydrogen or an H. All right, that's how we can just instantly tell it's an acid, something that starts with an H. Now, a bases typically end with an OH. So if it ends with an OH, it will be a base. I do want to make a little kind of disclaimer. So there are different types of bases that do have hydrogens and don't have OHs. You will learn that later on. For right now, for kind of where you guys are at, you're just learning the different bases. You're kind of learning bases as the fact that they just end with an OH. However, there are different types of bases that do not end with OH, like, for example, ammonia, NH3. However, I highly doubt you're going to see that in the very beginning of chemistry. That's kind of later on. But for now, let's kind of just focus on the fact that an acid starts with an H, a base ends in OH. And then how we form a salt, I'll give you a really quick example of what a salt is. This is known as table salt, so NaCl. So for a salt, it's always going to be an ionic compound. So an ionic compound, if we recall, is a metal with a positive charge combined with a nonmetal, which is negatively charged. So typically your salts will be, well, for sure your salts have to be ionic. They have to be an ionic compound, as well as you'll see that they typically form, they're typically mixed with groups 1 and 2, and then they're actually combined with halogens or any polyatomic atoms. So I'm going to say it again. So any sort of salt, our metal will typically come from groups 1 and 2. So groups 1 and 2. And then our nonmetal could be any sort of halogen. And I've sometimes also seen them as any sort of polyatomic atom. Really just depends on what we're kind of predicting our products or what we're starting off with our reactants. So right then and there we know. So as I said, a neutralization reaction is going to be an acid plus a base, and that gives us a salt and water. Really lock that into your mind. That's really going to help you out. All right, let's try some. So looking here, we'll see, okay, we have our acid, right? It starts with an H. So this is our acid. We have our base because it ends in OH. And we're going to do that whole inner, outer sort of method that I have. So looking at this, let's do the inner with the inner to form our salt. And we know that water is still going to form. So looking at the inner with the inner, we'll see that strontium, or Sr, has a 2+ charge. And then, by the way, remember that inner with the inner, outer with the outer sort of setup, you're going to have an ionic compound as well. So we'll have something that's positive, then the negative, and that's how you know how to kind of set this up. We wouldn't have placed CO3 first and then strontium. That wouldn't be the case. They never kind of work that way. It's always positive, negative. How I always like to kind of remind it, my cute little way of remembering it. You want to be positive before you're negative, right? We want to think positive before we think negative. So that's kind of a cute little way to remember ionic compounds. So then now looking at strontium with the 2+ charge, I'm going to now bring down our carbonate with a 2- charge. And right then and there, that's balanced. So that is our salt. And then, of course, we'll add water, but I'll still show you how we found water. So water comes from the outer with the outer. Remember, we're not going to bring any of those subscripts down. So that's where we have one of our hydrogens and our OH- come in, and those kind of fuse together or form together to form that H2O. Like I said, we never bring these subscripts down. That was just there to balance that initial compound. All right, and there we see, okay, that's an acid and base neutralization reaction because it formed a salt and it formed water. And this would be our end result. All right, let's try a couple more and then we'll get into molarity. So this is now going to test our skills on remembering how to name acids and compounds as a whole. So remember, anything that's an acid that has hydro in front, if we recall, hydro means that there is no oxygen in that acid. That's what that prefix means. So looking at hydro, there is no oxygen whatsoever in this acid. And then so I know, okay, that there's no oxygen. Then now I'm going to look at bromic. And then brome or bro, is going to be bromine or bromide. So that bromic acid means it's Br, and then it's an acid, so it has to start with a hydrogen. So right then and there, HBr. Not bad. And then I'm going to add that to the next thing, barium hydroxide. So barium has a 2+ charge. Hydroxide, or OH, has a -1 charge. And I'm going to balance this out. So this 2 goes down, and we'll have barium and our hydroxide in parentheses, N2. All right. So there we have our acid plus our base. Acid because it starts with a hydrogen, base because it ends in OH, and we're going to form that salt and water. So once again, inner with the inner, outer with the outer. So inner with the inner. And remember, this is going to be, you want to think positive before you think negative. So positive before you think negative. And then I'll see the barium is right here. Barium, we said, has a 2+ charge. Bromine has a -1 charge. And that 2 is going to lasso or kind of be given to that bromine because it needs 2 more. So then our salt will be barium bromide. And then we'll see that we're going to still form water. How we form water, just to show you again. We'll have that hydrogen come in first, and then that OH minus coming in as well. Those will form our water. And here we will have our neutralization reaction, where we have our acid, hydrogen in front, plus our base, ends in OH, forming our salt, because this is ionic, right? Positive, negative. And then we'll have our water. All right. That was messy. All right. Let's try a couple more. So now we don't have a prefix or anything that says hydro. So that tells us that there is going to be oxygen. It states that it's sulfuric acid. So if it ends in ic, it goes with the 8. So ic and 8. So then I know that sulfate is what I'm actually using. Remember, sulfate is SO4 with a 2- charge. And then it's an acid, so that means there has to be a hydrogen in front. So then I'm going to put that hydrogen in front with a positive charge. We'll balance this out. So this 2 has to then lasso down to that hydrogen, and this would have been H2SO4. That is our sulfuric acid. Next, I'm going to look at sodium hydroxide. So sodium is an Na with a positive charge. Our hydroxide is OH with a negative charge. They're balanced. So right then and there, that's our base. Once again, let's form that salt with our inner and outer with our outer trick. Think positive before you think negative. And I'm going to look at this as Na with a positive charge and SO4 with a 2- charge. They're not balanced. So I'm going to put that 2 for the Na. And now we'll have Na2SO4. And then lastly, we're going to form that water. So outer with the outer. This 2 subscript does not come down. So this is just H with a positive and OH with a negative. That's going to form our water. And this is going to be our overall reaction. So remember, we said that this was our acid because it starts with a hydrogen. And then this is our base because it ends in OH. We form a salt because it's an ionic compound, plus, minus. And then we also know that this is water. All right. Let's go ahead and move on. And finally get to molarity with my interesting little example here, my delicious sweet tea. So let's just kind of talk about molarity and understand what in the world is molarity. Why do we even care about it and whatnot? So we've all kind of heard of concentrations. Like, let's say how highly concentrated your orange juice is, right? So that's kind of something that we're looking at. Molarity is it's really just another way or a unit per se to talk about concentration. So that's what I want you to think of. Molarity is really just telling you how concentrated something is, and so on. So with molarity, we then kind of think about solutions as a whole. So if you guys haven't covered this just two yet, I know everyone's on different parts, kind of just bear with me. I really recommend you kind of understanding this concept. You will get to solutions very, very soon. And let's just kind of dive in as to what a solution is, what a solute and what a solvent are, and how they relate to molarity as a whole. So let's go back to this cute little example that we have here of iced tea or sweet tea. So we have some sort of tea and we have some sort of sugar. And I'm going to just kind of place the sugar right here. All right, interesting sugar, but sure, that's our sugar. So our sugar is going to act as our solute because our solute is whatever you are dissolving. So those are typically your solids, by the way. So your solute is whatever you're trying to dissolve. And that's kind of what we have here. So this is going to be, the sugar is then your solute. And then your solvent is whatever is doing that dissolving. So it's, in this case, it's our tea because it's our liquid. That's what's dissolving our sugar, which is our solute. So like I said again, so solvent is whatever is doing the dissolving. So that typically is going to be like your liquid. So in our case, it's our tea. In other cases, it could be water. It could be ethanol. It could be a lot of different types of liquids. So now, what makes a solution? So our solution is going to be the sum or the whole entire combination of our solute and our solvent. So this overall solution is the sweet tea, is the tea with the sugar, right? So that would be our solution. So I'm going to repeat this again to kind of really get the concept here. So our solute was the sugar. That is what you're dissolving. So solutes are always what you're dissolving. Solvents are what are doing the dissolving, or like the liquid that does the dissolving, which is our tea. And then our solution is the solute plus the solvent. And in our case, that's the entire sweet tea. Okay, now that we're kind of understanding this, why does this help, Melissa? So why this helps is looking at our molarity. It's not just moles over liters. It's specifically the moles of our solute divided by the liters of our entire solution. So understanding that concept, because it will come in later on, just in case it hasn't come in just yet, you will get to solutions very soon. So looking at this, our moles of our solute. So our solute, remember what it is, what is being dissolved. And then our solution is the entire solution of our solute plus our solvent. So it is extremely important to remember that molarity is moles over liters, because this will actually keep coming up a lot and it's constantly used as a conversion factor. So molarity, the unit is a capital M. And then you're going to see me kind of breaking this apart as capital M is equal to moles over liters. So whenever I pretty much see molarity, I instantly break apart the capital M to moles to liters divided by liters, just because this is your conversion factor. Remember, conversion factors allow you to go from one unit to another. That is why they typically have, actually they have to have two different units. So if they have two different units, they can be used as a conversion factor, because we can get to moles or liters depending on what the question is asking. So let's try some molarity questions and understand further what this is talking about. So let's look at something like this, that the question states, what is the molarity of a solution that contains 15 grams of NaOH per 500 milliliters of solution? All right, so it's asking us for molarity. So molarity, recall, is capital M, was our moles of our solute, so whatever is being dissolved, divided by our liters of our solution. So let's go back and see, well, we know what we're finding. What are we given? So what we're given is the 15 grams of NaOH. So 15 grams per every 500 milliliters of solution. So we have 500 milliliters of solution. So, I mean, we can probably tell which one is the solution part, but for looking at your solute, we said that it's typically going to be a solid because that's what's being dissolved. So a solid probably is going to be measured in grams because it's a type of mass. So then our solute would then be our NaOH. So note that it's not in the proper unit. Nothing is actually in the proper unit. We first have to make sure, is everything in the proper unit, and then we'll divide. So that's what we're actually going to do here. Let's go ahead and with our first step, just convert those grams of NaOH to moles of NaOH. So doing so, this is going to give us, let's see, we'll put the 15 grams of NaOH. And then remember, to go from grams to moles or even moles to grams, we have to use molar mass of that specific compound. So let's determine what our molar mass of NaOH is. So looking at Na, our molar mass of just one Na is going to be roughly 23 grams per mole. And then OH, so I'm just going to separate this apart as oxygen and hydrogen. Oxygen is 16, and then hydrogen is 1. So we'll add everything together. This would have been 10 and 2, 3, 4. So 40. 40 grams of NaOH per every 1 mole of NaOH. We'll go ahead and divide and see what we get. So 15 divided by 40. We will get a total of 0.375 moles of NaOH. Not done just yet. So that was just our moles, which is going to be on top. Now we have to determine how many liters do we have for our solution. So going back to our given, we have 500 milliliters. So using the metric system, we are going to have to change milliliters to liters. So let's show you how to do that. So now I'm going to change the milliliters to liters. And we have 500 milliliters of our solution. And we're just going to change that to liters. So I'm going to set this up with the proper units. So we want to cancel out our milliliters. So I'm going to align them across from each other. I'm also going to show you 2 different ways as to how to approach this question for milliliters. So how I typically teach this, if you guys have seen my videos for understanding the metric system. So I think of it as the base unit and the different unit. So the base unit is going to be the one with the 1 letter, or you could also think of it as liters, grams, or meters. And looking at our base unit, in our case, it's going to be liters. So the base unit is going to have the 10 to some sort of exponent. Since it's milli, that means it's going to be to the -3rd. And then milliliters, or the different unit, will always have 1. The reason why I typically show it this way is just because once you kind of get into more in depth with the metric system, it's hard to remember, do I multiply? Do I divide by 1,000? What do I do? So this is just kind of my way of never, having to be confused or not even know where to put the 1,000 or the 100 or whatnot. So this is my way, but there is another way. So there's another way of just knowing that there are 1,000 milliliters for every 1 liter. That's completely correct. So this would have been 500 milliliters for every, and then actually 1,000 milliliters on the bottom for every 1 liter. And by the way, this means the exact same thing overall. It's going to give you the same exact answer no matter which one you choose. So 500 divided by 1,000 or times 10 to the -3rd, they both give you 0.5 liters. Now that we have our proper liters, now we're going to divide everything that we just found. So remember that we're going to go back to molarity. And molarity, we said, was the moles of our solute divided by the liters of our solution. So I'm going to set that up. So we just found our liters. So that 0.5 liters is going to be on the bottom. And before we found our moles, which is right here. So these are our moles overall. And then now I'm going to just place that on top. So 0.375 moles on top. We'll divide these two, and that will finally give us our molarity. 0.375 divided by 0.5 would then give us a molarity of 0.75 capital M. Capital M just stands for molarity. So you could have written it as capital M, or you could also write it as mole per liter. Either answer is correct, and that would give us molarity as a whole. All right, let's try a few more, and I'm going to give myself a little bit of space. At this time, if you guys have any questions, feel free to leave a comment. If you're watching me on YouTube, feel free to leave in the chat. If you're, on the live streaming, then go ahead and leave a message in the chat if there's any questions that you guys have. Also, at this time, I'm also going to state if there is a specific topic that you want me to cover that maybe you have an exam on coming up, let me know. I love to hear from you guys. I love to just know what you're currently on and overall just what you want me to teach, because it's really, really helpful. I want more and more people to kind of be joining in on these sessions and really just getting the most out of these sessions, because this is your time. And I really, really just want to help you guys out to not only pass the class, but really succeed in chemistry overall. So that being said, if at any point you feel that you remember any sort of topic that you want to go over, let me know. I'm happy to hear. It's actually great to hear you guys' feedback and to know what you're currently doing. All righty. Let's jump into our next example where we have an unbalanced equation. So before even reading this, I'm just going to start off with balancing out this chemical equation. So looking at this, let's go ahead and kind of remember how to balance everything out. So my method was to write out all of our different elements that we have on either side. And so I'm going to write our hydrogen, and remember that any sort of polyatomic atoms, we are going to leave them intact. We are not going to separate them if they're the same on either side. So since PO4 and PO4 are the same on either side, I am not going to separate PO4 whatsoever. So I'm just going to rewrite that as PO4. Nothing changes there. Then now I'm going to look at, we have zinc. So these are all of the different elements that we have, and I'm going to line them up and place them in the proper order, in the same order, just to make it a lot easier for us to balance out these overall equations. So then now looking at our reactant side, we'll see how many hydrogen do we have. Looking at our subscript, there are 3. So we have 3 hydrogen. Next, for PO4, be careful, we do not have 4. That subscript does not tell us we have 4 PO4s. That just tells us we have 4 oxygen. Now, for the entire polyatomic atom, there's only 1 because there is no parentheses with a subscript telling us that there's more than 1. So whenever it's just PO4 and there's no subscript, like in this case, then we only have 1. Now with zinc, once again, there's no subscript, so only 1. Hydrogen, we have 2. PO4, as I mentioned before, this 2, since it's on the outside of your parentheses, that tells us there's actually 2 PO4s. And zinc, we have another subscript, and it tells us there's 3. All right, so that being said, let's go ahead and balance everything out. And I recommend, by the way, always leave oxygen for the very, very end. That's going to end up balancing itself typically. And then leave hydrogen second to last. So everything besides hydrogen and oxygen, balance that out first, then balance hydrogen, then balance oxygen. All right, just makes it easier. So I'm going to start off with, I'm going to see if I can balance out zinc right off the bat, and we'll see, will that work? So in our case, I'm going to balance out zinc, and we'll see that that would have been a 3 right in front of zinc. When I do that, that only affects the zinc, and I recount everything. And then now I'm going to see, okay, why don't we balance out our overall hydrogen? And I'll see that there's 3 on the reactant side. There's 2 on the other side. And I kind of want you to think of this as like, what's the common factor out of both of these? What can 3 and 2 both go into? And we know that's 6, right? 3 times 2 is 6. So I'm going to place a 2 in front of this entire compound. We cannot just place the 2, let's say if we wanted to balance out PO4, we can't just place the 2 somewhere in the center here. That doesn't work. We can't just kind of separate that compound. Instead, we have to always place it in front of the entire compound. So looking at this, now let's recount everything that we have again. That 2 would then multiply with our 3, making it a 6. So we now have 6 hydrogen. And then this 2, I want you to think of it kind of like distributing into both of these. So we now have twice as many PO4s. So we have 2 PO4s. And then we still have 3 zinc. So balancing this again, we'll see, okay, let's look at hydrogen. Well, how many do I need? On this side, I need 3 because 3 would then multiply with this 2, and that would make it 6. And then now we still just have everything else. And look at that, we're balanced. So now that we're balanced out, and by the way, note that I didn't really have to even do anything with oxygen or the PO4 because it just ended up balancing out itself. It sometimes does that. Sometimes that's how life is. It just balances out itself. If only always. So now going back to our example here, now that we have our balanced equation, I'm going to just look at what we're given, what we're solving for, and go from there and develop a plan. So it's just to determine what we're given and what we're finding. So looking at this question, how many liters of a 3 molar phosphoric acid solution are required to react with 4.5 grams of zinc? So, all right, we're given 4.5 grams of zinc. We're also given a molarity. So if they're giving us a molarity, that must mean that's our conversion factor because that has 2 units, moles divided by liters. So I'm going to actually break that apart. Instead of putting a capital M, I'm going to just break this into moles per liter. And that's going to be of our phosphoric acid. All right, what are we finding? So it's asking us how many liters of phosphoric solution are required to react with zinc. So we need liters of phosphoric acid. So this is all that we're finding here. This is 4 phosphoric acid. So looking at this, where do I start? So looking at our given, we're always going to start with the one that only has 1 unit. So I'm going to start off with the 4.5 grams of zinc. And even before doing so, let's go ahead and determine our plan. So let's kind of plan this out and see what we're going to be doing. So as I mentioned, we're going to go from grams of zinc to something else, right? We want to eventually get to our liters of phosphoric acid. So if we're trying to get from grams of zinc to somehow get to liters of phosphoric acid, note that we are changing our compound. Right? This is good old stoichiometry again. So going from grams of zinc to liters of phosphoric acid, if you're changing your compound, what do we need? We need a balanced equation, which we just found. So that's why we were going to do a mole to mole ratio in just a second. So looking at this, I'm going to see that, okay, we have grams of zinc. So then we could figure out how many moles of zinc there are using the molar mass of zinc. Next, we have our balanced equation. So we can do a mole to mole ratio to change our compound. So that's exactly what we're going to do, going from moles of zinc to moles of phosphoric acid. And lastly, we're asked to figure out how many liters are of phosphoric acid. So how do we find that? We're given one more thing. We're given our molarity. So this conversion factor here allows us to go from moles to liters. So that's what we're going to use at the very end. We're going to use liters of phosphoric acid from our molarity. So just to kind of really lock this in, the first step, going from grams to moles, we will use our molar mass of zinc. Once we have moles of zinc, we're going to use our next conversion factor, which is a mole to mole ratio found on our balanced equation. Last, to get from moles of phosphoric acid to liters of phosphoric acid, we would then use our molarity of phosphoric acid to determine our liters. That will be our conversion factor overall. So let's set this up. Let's go ahead and begin with the 4.5 grams of zinc. And we'll look for zinc on a periodic table and see what is the overall molar mass of zinc. And looking at my periodic table, I see that it's 65.37 grams of zinc per every 1 mole of zinc. And that's just our first step. That's our first molar mass step. Now that we can see that our grams of zinc and grams of zinc would then cancel, we're at moles of zinc This is a Z, by the way. So I'm going to look at our balanced equation in just a second, but let's kind of write those units to just know where we're placing everything. So moles of zinc would be on the bottom, and moles of what we're actually solving for, what we're looking for, of phosphoric acid would be on top. So let's look back at our balanced equation and see how many moles of zinc and how many moles of phosphoric acid we have. So we have 3 moles of zinc for every 2 moles of phosphoric acid. So going back here, we'll see, okay, we said we had 3 moles of zinc for every 2 moles of phosphoric acid. Now that we have our proper compound or proper acid in this case that we're solving for, I'm going to cancel out our units that we know. Moles of zinc cancel. We're now at moles of phosphoric acid. And our last step is to use the molarity of phosphoric acid as our conversion factor to finally give us our liters. So that's exactly what I'm going to place here. And let's actually make a quick little note here that our molarity is that 3 or whatever number of our molarity we have goes with the moles, and that's per every 1 liter. All right, that's going to help us kind of understand that, because you could actually flip this around. It doesn't have to be exactly where you're always going to multiply. Sometimes you'll have to divide by the moles, and I'll show you that right here. So we're going to divide by the moles. So we'll have 3.0 moles of phosphoric acid for every 1 liter. This is our molarity. It's just kind of flipped around. And we're allowed to do that just because it is a conversion factor. We're using it as a way to kind of just get to that liters overall. And that's exactly what we get here. So this gives us our liters of phosphoric acid. So what we're going to do is multiply straight across and divide by everything else. So I'm going to say multiply straight across and then divide by everything else. All right, so looking at this, we'll have 4.5 times 2, giving us 9, and then divided by really 3 times 3, so 9 times that 65.37. So 65.37 times 3 times 3, or 9. We'll divide these two. And this will give us 0.015 liters of phosphoric acid. And just to double check, let's go ahead and look at how many sig figs we should have. Always going back to sig figs. So everything just had 2 significant figures, right? That 4.5 is 2 sig figs, same with that 3.0. And so I'm going to round to 2 sig figs. Let's double check that this is 2 sig figs. And yes, it is, because these leading zeros do not count. So we only have 2 sig figs. Moving on to another example. So looking at this next one, it states how many grams of aluminum are required to react with 35 milliliters of a 2 molar solution of hydrochloric acid, or HCl. Now, we once again have to balance out this chemical reaction. So let's go ahead and do that right off the bat. As mentioned, we're really just going to write everything that we have, all of our elements that we have. So we have H, or hydrogen, chlorine, and aluminum. And I'm going to mirror that on the opposite side. And then now we'll just count how many of each reactant we have on either side. All right. So we have 1 hydrogen on our reactant side. We have 1 chlorine as well. And we have 1 aluminum. So 1 of everything. And then now looking at our products, we'll see there are 2 hydrogen. We have 3 Cls, and we have 1 aluminum. So balancing this out, really it's just the reactants that need everything. So I'm going to start off with everything besides hydrogen or oxygen. So I'll start off with the chlorine. So looking at chlorine, I'm going to place a 3 right in front of HCl. And then we'll see what that kind of would then form. So then now what happens is, okay, this will then form 3 hydrogen, right? This is being distributed. And we'll have 3 chlorine, but we only have 1 aluminum. So, okay, we're not balanced anymore. We're still not balanced. So now looking at hydrogen, sadly, nope, doesn't really work out. So what I'm going to try next is I'm going to say, okay, what if we get a common factor? So 3 and 2, they both multiply to give us 6. So what if I made hydrogen 6? So if I were to do that, I would erase this 3, and I would now make a 6 here. And I'd say, okay, well, that's going to distribute as well. So hydrogen is now 6, and chlorine's also 6. Aluminum still hasn't changed. And then now looking back at our chlorine on the opposite side, I'll see that, okay, there's 6 on our reactants and only 3 on our products. So what will multiply with that 3 to give us that 6? I know 2 will. So if we have a 2 there, then I'll see, okay, well, that will then distribute to each. So aluminum is now 2, and chlorine is 2 times that 3, right? This 3 subscript. So that would be a 6. And lastly, we still have hydrogen as 2, so we're still not balanced. So I'm going to balance out the aluminum on the left-hand side or the reactant side, and we'll see that we just need 2 aluminum. So this is 2. Lastly, we'll have 6, 6, and 2. So at least that is complete. And then now looking at hydrogen, we need 6 hydrogen on the right-hand side or the product side. So what will multiply with that 2? A 3 to give us a 6. Checking everything else. Yep, we're balanced finally. There's some of these that kind of like look a lot easier than they seem until you actually do it, right? I'm like, oh, no polyatomic atoms. It has to be easy. Sometimes it can take a little bit. So I definitely recommend writing everything out beforehand. Sometimes you can do this in your head. For this one would have been like a little bit trickier, I'd say, to do in your mind. But if you're, not to that point where you're doing that in your head, that's totally fine. Writing it out is still going to work out. All right. So let's look at what we're finding. So looking at our given, we're given 35 milliliters of HCl. We're also given the molarity of HCl. So we're given 2.0 molar or capital M. Remember, I'm going to change that to moles per liter because what molarity is. So now looking at this, and by the way, I'm actually going to just put 1 liter here because this is saying 2 moles per every 1 liter, just to help you understand that a little bit better. And this is going to be of HCl. Let's see what we're finding. So it says how many grams of aluminum. So how many grams of aluminum are exactly what we're solving for. Let's develop our plan. So our plan is going to be going from milliliters of HCl to grams of aluminum. So we're going to start off with our given that has the 1 unit because that's what we're going to start with. Anything that has 2 units is then going to be used as our conversion factor somewhere in the middle. So we'll have milliliters of HCl, and we're going to go to somehow, some way get to grams of aluminum. So our first step is to always convert your milliliters to liters whenever you're using molarity. So I'm going to convert that instantly to liters of HCl. Once I do that, I can then get the moles of HCl using my conversion factor or molarity. So then I'll get moles of HCl. And then from there, we're at moles of HCl. We want to change our compound entirely, so we have to use a mole to mole ratio. So using a mole to mole ratio at this point, we'll get aluminum. And lastly, we'll be able to go from moles to grams using the molar mass of aluminum. And let's just jot down all of these in-betweens and what all of our conversion factors are. So going from milliliters to liters, we're going to use that metric system conversion again. And then now looking at our liters to moles, we'll use the molarity of HCl that was given. And then next going from moles to moles so moles of HCl to moles of Al or aluminum, we will use the balanced equation using our mole to mole ratio. And lastly, going from moles to grams, we'll have our molar mass of aluminum. So we have 1, 2, 3, and 4 conversion factors in this example. Let's start it off. So looking at the 35 milliliters of HCl, I'm going to convert that instantly to liters. So as mentioned, you could either put 1,000 milliliters for every 1 liter, or you can write it as 1 milliliter for every 10 to the negative third liters. It means the exact same thing. And this is still of HCl. All right, and then moving on to our next conversion factor, since our milliliters of HCl cancel, I'm going to place the liters of HCl on the bottom so they can then cancel on the top, and then we'll get our moles of HCl. We're going to use our molarity that was given, so the 2.0 moles over 1 liter of HCl. Our liters and liters then cancel, and then we'll have our mole to mole ratio. Placing the moles of HCl on the bottom and the moles of aluminum on top, let's go back to our balanced equation and figure out how much of each we have. So looking back here, we have 6 moles of HCl for every 2 moles of aluminum. That's exactly what we're going to use to our mole to mole ratio. So we said 6 moles of HCl for every 2 moles of aluminum. Almost done. So then now going from moles and moles of HCl, those cancel. We're now at moles of aluminum. So we just need the molar mass of aluminum to finally get this question done. So we'll have 1 mole of aluminum. And aluminum's molar mass, looking at our periodic table, is 26.98 grams of aluminum. Moles and moles of aluminum cancel. We're finally left with grams of aluminum, and we will do the math. So I'm just going to focus right now on the top. So really just focusing on the top. I'm going to actually multiply everything out right here. As we'll see, that's kind of what I'm trying to circle or take apart. So multiplying everything on the top, we'll do 35 times that 10 to the negative third times 2 times 2, or 4, times that 26.98. That then gives us 3.7772. And then I'm going to divide this by the only number that's on the bottom, which is 6. When we do that, this would then give us 0.629533 grams of aluminum. I'm going to go back and see what was our given and how many sig figs should I be rounding to. So each one of these givens, luckily, was 2 sig figs. So that's exactly what we're going to round to. We're going to round to 2 significant figures. So going back to what we had before, our 2 sig fig mark would have been right here because leading zeros do not count. So this would have been 0.63 because this 9 allowed that 2 to round on up. And this would have been 0.63 grams of aluminum, which is our final answer. All right. So that's all for today. Thank you so much for everybody who came and joined us today. And if you're actually watching the replay later on, make sure that you let me know in the comments what you're struggling with, what you want me to teach next. And then please, guys, keep sharing my videos. I really want us to get to 10,000 subscribers, keep growing this chemistry community. And I also will be doing a 8-hour live session if we get to that 10,000 subscriber mark, just to really help you guys with finals overall. Definitely leave in the chat if you're on the live stream right now. Leave a chat. Let me know what you guys need help with. Anything that like you really just want me to go over. If you have specific questions, if you have an exam coming up, let me know, guys. I really like to just know what you're on so I can teach that for next Sunday, because I don't know right now what I'm teaching next Sunday. Emmy says, thank you so much, Melissa. Super helpful once again. Oh, thank you. I'm so glad. And then let me just kind of look at this. The last problems you did are kind of struggle with most, especially when there are more numbers and units involved. I always had a hard time setting up the equation correctly, especially when it's incorporated into a story problem. Yeah, word problem. Looking forward to the next one. Oh, thank you. Thank you guys for sharing. Thank you for all your feedback. And just overall, seriously, guys, just thank you for everything, all of your amazing feedback and your comments. I truly, truly appreciate it. And I will see you guys next Sunday. Make sure to reserve your spot today. And I'll be getting in contact with you just to tell you what in the world I'm going to be teaching. All right. So have a beautiful Sunday and a beautiful day, guys. See you next time.